Math 1314, section IC1, spring 2022, Tyler Junior College. Section 5.3, relations, functions, and function notation. Video 3, function notation. This is the final video in the series for section 5.3, and the content of this is actually pretty easy. There's a couple of types of problems that might make you go, but I'm going to show you how to get through all of them. So let's start with what I mean by function notation. Suppose we have a relation, set of ordered pairs, that is also a function, which means every x has exactly one y. To emphasize the particular y associated with a given x, let's widen this a little bit. I forget what I just said. All right, to emphasize the particular y associated with a given x, we can write y equals f of x, which is read y equals f of x. It's specifically this phrase here, or this notation here, is read f of x. Now, it's important to point out two things real quick. Number one, that is not f times x. It is not a multiplication problem. The f is the name of the function. It's almost like a verb, and the x is the object that you're performing that function on. It's read f of x. And number two, f is not a variable. It's the name of the function. So you never solve for f. You never substitute a number for f. F is just the name of the function. And again, this is read f of x. So each ordered pair can be thought of as x comma f of x instead of just x comma y. In particular, if there's a formula that tells us how to turn an x into a y, we write f of x equals that formula, and this is called function notation. When you have f of x equal to something, as I'm about to demonstrate in just a moment. Let's put in boxes the important things here. All right, so let's take a look at an example. Consider the following function. The set of ordered pairs 0, 0, let's highlight and move as I say these just for focus. The relation containing the ordered pairs 0, 0, 1, 5, 2, 10, 3, 15, 4, 20, 5, 25, and so on. So this relation, the set of ordered pairs, goes forever. A, determine the formula that turns each x into its corresponding y. Misspelled the word corresponding there. Determine the formula that turns each x into its corresponding y. B, write the function in function notation. And C, evaluate f of 6 and f of 99. Once you get past part A, this is actually really easy, because part A is asking you what rule or what formula are we using that turns each x into a y. If you were to think of this as a table where we have 0, 0, 1, 5, 2, 10, 3, 15, 4, 20, 5, 25. I mean, there's a clear pattern in both the x and the y column going downward. The x's are going up by 1, the y's are going up by 5. But when you're looking for the formula or the function, if you will, the question is, what's happening horizontally? What do you do to 1 that 0 turns it into 0? What do you do to 1 that turns it into 5? What do you do to 2 that turns it into 10? And you want to do the same move all the way down. And it may be fairly obvious, but if it's not, I'm about to tell you. The move or the rule is we're multiplying the x value times 5 to get the y value. In other words, to get the y for each ordered pair, that's equal to 5 times whatever the x is. Now, it's not always this obvious. In fact, most of the time, it's not obvious what the actual function is when all you're given is ordered pairs. But I wanted to set up one that was fairly transparent. At least at this point, it should be fairly obvious that for each ordered pair, the y is 5 times the x. I'm going to say that again, and I want you to watch what I highlight. For each ordered pair, the y is 5 times the x. So if you can verbalize it, you can almost always put it into function notation. Speaking of which, we haven't put in function notation yet, but to write the function in function notation, all you have to do is write the exact same thing I did, except replace y with f of x. Excuse me, that's still drawing boxes. Except replace y with f of x. And this, which I'm about to put a box around, is the function notation for this relation, assuming that the pattern continues indefinitely. And now that we have the function written in function notation, f of x equals 5x, we can evaluate the function at other x values. The number that you write inside is often called the input, and the number that comes out is often called the output. In this case, to evaluate f of 6, all we would have to do is take our function and replace the x with 6. So instead of 5 times x, we would write 5 times 6. And there's a variety of ways of writing that. The dot is 1. 5 times 6, of course, is 30. Which kind of means that in our table, if we had a 6, it would be paired with a 30. And the same thing for f of 99. Because our function is f of x equals 5x, then f of 99 is 5 times 99, which I believe is 495. Which means as an ordered pair, 99 would be paired with 495. If you have the function in function notation, the thing in the orange box, then it's pretty easy to do these types of problems because all you're doing is putting in a number for the x and working out the problem. There are many questions we can ask concerning function notation. The first of which is, given a function, can we write it in function notation, which is equivalent to asking, what's the formula? That's what we did back here. When we saw the empirical evidence in the top orange box, the ordered pairs 0, 0, 1, 5, 2, 10, etc., we were trying to figure out what's the rule or what's the function that turns each x into its y. The second question we could ask is, given function notation, can we determine an ordered pair belonging to the relation? That's what we did in part C. In part C, we had the function notation already from part B, and we used that to generate 2 ordered pairs, specifically the ordered pair 630 and the ordered pair 99, 495. You can almost think of a function in function notation as an ordered pair generator. You got a function in function notation like f of x equals 5x. You need some ordered pairs. Stick numbers in, get numbers out. Every time you do that process, you've created an ordered pair. And the third question is, given function notation, what is the graph of y equals f of x? Because after all, a function in function notation is a function, which is a relation, which is a set of ordered pairs, which can be turned into dots and made a graph. So later on, we'll be doing that. In fact, for the rest of this video, we'll focus on the second question. Given function notation, can we determine an ordered pair belonging to the relation? And the other questions will be addressed in future videos. All right, so let's take a look at some specific examples that start out by giving you a function in function notation. Suppose f of x equals 3x plus 5. A, evaluate f of 2. B, evaluate f of w plus 4. And C, for what values of x does f of x equals -7? Well, of these, I think the first one is clearly the easiest question. I invite you to pause the video and try some of these. You're always welcome to do that, even if I forget to mention it. But if we want to evaluate f of 2, all I have to do is go to my original function and replace the x with 2. Now I could use a dot to indicate 3 times 2, but I'm going to use parentheses this time. And then the order of operations says that we're supposed to multiply first. 3 times 2 is 6. And then after that, do the plus 5. And so as a conclusion, we can say that f of 2 equals 11. Now, every time you do a function notation problem, you generated an ordered pair. As an ordered pair, this would be 2, 11. The input is the x, the output is the y. Now, the second one looks harder than it is. Evaluate f of w plus 4. When your input is more than a single number, nothing changes. You just have to proceed with caution. Now, there is a systematic way to do this, and I'm going to show you this. And maybe you can do this without the systematic approach. But here's the systematic approach. It does involve writing something and erasing something, so you've been warned. The systematic approach to putting any input into any function is to first write the function as is, 3x plus 5, but leave some room where the x is. Then erase the x, just the x, please. And in its place, put an open set of parentheses. Now, when you do this, you're preserving the structure of the function. Right now, I've got a setup that says 3 times something plus 5, which is exactly what the function says, 3 times something plus 5. So replace the x with empty parentheses, and inside those parentheses, write whatever the input is. In this case, w plus 4. If you look at the original function and the problem we're currently doing, you'll see what's going on here. In the original function, we used to have an x, there was an x inside the parentheses, which showed up in the formula on the right. But in the current problem, instead of an x, we have a w plus 4, which means in the formula, instead of an x, we write a w plus 4. The only catch is you should put it in parentheses. Why? To keep everything in check. Specifically in this example, notice that when I put the w plus 4 in parentheses, it was preceded by a times 3. This sets up the distributive property. This is the reason why you want to use parentheses when you substitute things into functions that are more than just single numbers. Because if there's any multiplication that preceded it, then it's going to invoke the distributive property. 3 times w is 3w. 3 times 4 is 12. And then we still have the plus 5 at the end. And then we gather like terms. 3w is the only w term. 12 plus 5 is 17. We cannot combine the 3w and the 17. They are not like terms. One has a w, one does not, which means this would be our final result. Put boxes around the final results. All right, so don't be afraid to substitute something bigger than a single number into a function. It plays out the exact same way. You just have to proceed with caution. All right, and for the last one, it's kind of a backwards problem. For what value of x does f of x equal -7? Well, notice on this problem, we're not told what goes into the function, but we're told what comes out of it. Whenever you have a, for lack of a better phrase, backwards problem, where instead of giving you the input and asking you the output, I give you the output and ask you the input, all you have to do is replace the function notation with what it equals or what it represents. And in this problem, f of x is represented by 3x plus 5, which is equal to -7. And now we just have to solve this. Well, it's not that hard. We would subtract 5 from both sides. This is just a linear equation. That would cancel the 5s on the left, leaving 3x equals. On the right, we would get -7 minus 5 is -12. And then if we continued, the only thing we would have to do to finish solving 3x equals -12 is divide both sides by 3 and give us a solution of x equals -4. Now keep in mind that when I get x equals -4, I've actually found the front end of an ordered pair. The ordered pair in this case would be the input is -4 and the output is -7. I didn't do the input and output on part B, but if I did, the input would be w plus 4. The output would be 3w plus 17. Let's take a look at another example that's a little more involved, and then we're going to make a few observations and comments. All right, so for this one, we're going to suppose that we have a quadratic function. Excuse me. Now, we've talked about quadratic equations before, where you had something like this equal to some value and then you solved it, but this is not a quadratic equation. This would be called a quadratic function. It's a function that's equal to a quadratic polynomial. Remember, quadratic means highest powers too. But the fact that that g of x contains an x squared. By the way, g of x is equal to x squared minus 5x plus 6. I should probably say that. Beside the fact that it has an x squared, it really doesn't change anything that we're going to do. For example, evaluate g of -2. Well, this just means that I'm going to put -2 wherever there's an x. Now, there is a place where people will make a mistake here. If you're writing this down, stop writing and watch this, because I want to show you what people would do wrong. At the very beginning where it says x squared, what some people will do is they'll write -2 and then put a square on it. And at that point, you've already missed the problem. Why? Because when you see a square or any power, It belongs to the thing immediately to the left of it. And what is immediately to the left of this power? The 2. But what was x representing? The -2. The -2 is supposed to be getting squared. When you write something like -2 squared like this, you're not squaring -2. What you're doing is squaring 2 and then subtracting it from something, or making it negative. So the answer to that problem is actually -4. To square a negative number, you have to put it in parentheses. Otherwise, the negative is not getting squared. Now, all of this can be easily avoided all of these problems can be easily avoided if you use the same gimmick I showed you on the previous problem, where you write the function as is, and then on the right side, get rid of every x and replace it with empty parentheses. So we'll replace the first x with empty parentheses, and we'll replace the second x with empty parentheses. I can't think of a single situation where doing this is going to cause trouble. More often than not, it might make the problem look tougher, but it will always set it up correctly. So you can always do a function problem by removing all the x's from the formula and replacing them with parentheses. And while you're at it, get rid of the x inside of the g of x, and then just replace it with what the input is in this problem, which in this case is -2. So I'm going to fill in every parentheses with -2. And doing so will always set up the problem correctly. And then just work it out. -2 squared is +4, followed by, and here's where you have to have a little bit of a flexibility in what you see here. This looks like -5 times -2, but if you were to look at it in isolation, it also looks like -5 times -2. And you can think of it that way. -5 times -2 is +10. And then +6. And of course, all that is equal to 20. Which means as an ordered pair, we just generated the ordered pair -2, 20. You don't have to say, I made this ordered pair. If the question was, what is g of -2, then its answer is 20. But together, the -2 and 20 would make an ordered pair. For part B, for what values of x does g of x is equal to 0? Well, this is just like the third problem back here where we put the function equal to -7 and solved. We can do the same thing here. We can put x squared minus 5x plus 6 equal to 0 and solve it. But this is a quadratic equation, and we've had plenty of experience with those. You can solve it using the quadratic formula, or you can try to factor. This guy will factor into x minus 2 times x minus 3. Then you would set each factor equal to 0. X minus 2 is equal to 0. X minus 3 is equal to 0. And then solve to get x equals 2 and x equals 3. Now, as a question asking you to do something, it's over, because the question is, for what values of x does something happen? Well, when we said g of x is equal to 0, that gave us x equals 2 and x equals 3. Could we write these as ordered pairs? We could. But it wouldn't be 2, 3. It would be 2, 0 and 3, 0. We found the x's that created an output of 0. And then for the third part, evaluate g of x plus h. This is kind of like the second part back here, f of w plus 4. But the fact that there are no numbers here really doesn't change how you're going to approach the problem. Let's do it in this color. What is that? How about this? There we go. If we wanted to evaluate g of x plus h, don't let the size of the input intimidate you. You can always do the following when setting up a function. Write the function as is, but space it out whenever there's an x, because they're about to get replaced with parentheses. Then get rid of each x and replace it with parentheses. Let me make this parentheses a little wider. By replacing each x with parentheses, you are preserving the structure of the original function, something squared minus 5 times something plus 6. But by replacing the x's with empty parentheses, you are providing yourself a space to write the input, x plus h in each parentheses. You know what? I did not leave myself enough space to finish this. So we're going to do it on an extra page. 1 second. This problem would be continued on page 11 of this PDF. Now in the video, it's going to look like the next page, but when I save it as a PDF, it'll be page 11. So we're doing that problem. We are doing g of x plus h, and that was set up as x plus h squared minus 5 times x plus h plus 6. So all the x's got replaced with parentheses with an x plus 6 on the inside. Now, the setup is easy. The tricky part about this is the simplification. And just to let you know, this very thing that I'm setting up right now is a key move in the beginning of a calculus concept. I know this is not a calculus class, but a lot of people who are taking college algebra are taking it en route to taking calculus, and therefore consider this a warning about stuff that's going to happen in the future. Now, that doesn't mean you don't have to be able to do this type of problem if you're not going to take calculus, but every one of you is on a path towards calculus, whether or not you knew it. You may not go all the way down that path, and that's okay. But I have to do the things that prepare students who are going towards the calculus path. But this problem is manageable, even if I didn't even say the word calculus. Why? Because I know how to do all of these things. The second parentheses I'm not worried about. That's just the distributive property. We'll handle that when we get there. But where everybody will make a mistake if you are not careful is this. Because a lot of people look at that and assume, warning, what I'm about to write is wrong, assume that they can do this. You cannot. You cannot distribute a power across addition or subtraction. So what can you do? Well, do what the 2 means. What does it mean to square something? It means to multiply it times itself. So we'll do that in a moment, but let's go ahead and do the distributive property on the second parentheses. You can distribute multiplication across addition. Negative 5 times x is negative 5x. Negative 5 times h is negative 5h. And we still got the plus 6. And now, what do we do about the first 2 parentheses? Well, in a word, FOIL. First, x times x is x squared. Outside, x times positive h is positive hx. It doesn't matter what order you put them in, but when I have letters next to each other, I like to put them in alphabetical order if I can. The inside part of FOIL is positive h times x, which is also positive hx. And the last part of FOIL is positive h times positive h, which is positive h squared. And then all the other pieces that followed, the minus 5x, the minus 5h, and the plus 6. Then we look for like terms carefully. I'm going to highlight like terms as I find them, starting with the x squared. Well, that's the only x squared out there, so x squared. Okay. Now let's find the hx terms, and there is a second one right next to it, but those are the only hx terms, and there are 2 of them. So hx plus hx is 2hx. Or you can think of it as 1hx plus 1hx equals 2hx. There's really no need to write the implied ones. Okay. Let's go to the next term and find its like terms. H squared. That's the only h squared around. So plus h squared. In fact, the rest of the terms don't have any like terms to combine with. This is the only x term. This is the only h term. This is the only constant term. So all we can do at this point is write down the rest of the terms. Minus 5x, minus 5h, plus 6. And as incomplete as it may look, that is our final answer because there's nothing left to do. So messy, but don't be surprised when you see one like that in your homework. All right, let's go pick up the comments here. Closing comments. Number 1, the name of a function doesn't have to be f, and the input variable does not have to be x. For example, the function d of t equals 10t measures the distance d of t in meters a runner travels in t seconds if she's running 10 meters per second. Evaluate and interpret d of 5. If you think I'm just doing this problem at random and that it's not in the homework, you would be mistaken. There's one like this in the homework. Evaluating D of 5 is actually pretty straightforward. Don't let the D or the T throw you off. It's the exact same protocol. Replace the T with the 5. 10 times 5 is 50. But what does that 50 mean in the context of this problem? Well, according to this problem, the T, the number going in, is how long you run, and the output, D of T, is how far you traveled. So we could say that after 5 seconds, and we could even write T equals 5 seconds because that's what the T was, the input. The runner has traveled, we'll say D of 5 equals 50 meters. Most functions, a lot of functions have some sort of contextual meaning. All right. Comment number 2. In general, though, the input can be thought of as the first coordinate of an ordered pair, and the output can be thought of as the second coordinate, which normally are called X and Y, but they don't have to. The input is the first coordinate, and the output is the second coordinate. So, for example, consider the function written as 4 ordered pairs, 1, 9, 2, 9, 3, 10, and 4, 11. A, evaluate f of 3. Well, when you see something like f of 3 without a formula, but rather a list of ordered pairs, you need to think, not think that 3 is the input and you're being asked for the output. 3 is the first coordinate, you're being asked for the second coordinate, and then find an ordered pair that matches that. Since 3, 10 is the ordered pair in the function, then we would say f of 3 is equal to 10, without knowing how the 3 got turned into a 10. And it can work backwards. If I said solve f of x equals 9, then we're thinking that the input is what we don't know, the output is 9, and so the first coordinate we don't know and the second coordinate is 9. And then we go looking for, let me put this in a different color. And then we go looking for ordered pairs that have that structure. So we're thinking something goes in and 9 comes out, and we look for any ordered pairs that have 9 as the second coordinate. Well, notice there's 2 of them. Since there's 2 of them, this means that x is equal to 1 and x is equal to 2, because both of those are ordered pairs that have an output of 9, a second coordinate of 9. And third and final, some functions do nothing other than produce the same output regardless of the input. Such functions are called constant functions. Should be pluralized there, constant functions. For example, if h of t equals 10, then that's it. Evaluate h of 1, h of 15, and h of a plus b. Well, when you have a constant function, there's nothing to figure out. This function says, I don't care what number you put in, I'm going to give you out the same answer every time. H of 1, 10. H of 15, 10. H of a plus b, I'm a constant function. I constantly give you back the same answer, 10. So don't panic when you see a function whose formula doesn't involve the variable. It's an easy function. All it says is, I don't care what number you give me, I'm going to give you back a 10.